Hello, this is chapter 23, where we're going to look at the increased destruction of erythrocytes. This is pretty much going to start off with the theory of hemolysis. And I think you guys have heard of this before, especially in phlebotomy, when we talked about how careful you have to be using, larger lumens of needle to make sure that the, just cells aren't destroyed and things on the way through. This type of hemolysis can also happen inside the body. Okay, so that's what we're going to focus on today. Hemolysis generally just means the destruction of red cells. This can happen in a variety of ways. One of the ways, one of the things we're going to look at is hemolytic anemia. This occurs when RBC survival is so short that anemia develops despite the bone marrow trying to compensate. Okay, this could be autoimmune. It could be something where a mechanical issue, such as a prosthetic heart valve. There's a number of things in the body that could cause the blood cells to be destroyed, as you can see by this picture. So again, the bone marrow just can't keep up and compensate for the amount of hemolysis that is happening. So when this does happen, how does the bone marrow try? We know it can't keep up, but it does try. So when increased hemolysis occurs, there's a lack of oxygen being brought to the tissues because there's not very many RBCs, right? The cells in the kidney are going to sense that there is a lack of oxygen and make more erythropoietin. The erythropoietin is going to go to the bone marrow to try and increase the number of those red cells being produced and make up for the cells that are being destroyed. Elevated reticulocyte counts are definitely seen after this acute blood loss because the bone marrow is going to do everything it can to try and keep up. So that's an important piece, especially after a patient responds to iron therapy. If the bone marrow isn't able to keep up, the anemia will set in because there are too few red cells. Since these cells are being destroyed because of hemolysis, the anemia is called hemolytic anemia. So that's a little bit of background to hemolytic anemia and how the bone marrow tries to compensate for that. We're going to look at two different classifications, acute versus chronic. With acute hemolytic anemia, it's very rapid and it's usually an isolated episode. So whatever causes it disappears and goes away pretty quickly. One example of this is paroxysmal cold hemoglobinuria or paroxysmal nocturnal hemoglobinuria. In each of those cases, it's usually dependent on a few things, whether the patient's cold or if the patient's laying down at night. It can be intermittent depending on the situation that the patient is in. So that would be acute. It rectifies itself pretty quickly. With chronic, the RBC lifespan is chronically shortened, but the bone marrow is able to compensate and prevent the anemia as best it can. One example of that is glucose 6-phosphate dehydrogenase, which we usually call G6PD, is a case where we may see something like that. We have two additional categories that we can put these in, inherited versus acquired. We talked about these with the aplastic anemias as well, so this definition should make some sense to you. But one example of an inherited one, something that could be passed down to children by genes in the parents. And we'll talk about different types a little bit later. The acquired would be you are acquiring an agent that could lyse the cells, such as malaria. Okay, cells are not going to last real long with a malaria parasite in it. Here's an example of what malaria might look like inside of a red cell. We also have intrinsic versus extrinsic. Intrinsic is where there's abnormalities of the RBC membrane, enzyme pathways, or the hemoglobin molecule itself. Extrinsic is caused by the action of external agents, such as an antibody attacking the RBCs or prosthetic heart valve squishing the RBCs and causing them to be destroyed. Okay, so that would be a traumatic cardiac hemolysis if that were the case. So intravascular, inside the bloodstream, extravascular would occur inside the macrophages. So we have different types happening in different places. So another type is where a patient develops an antibody that causes red cells to be destroyed in the spleen. What type of hemolysis is this? It would be acquired, extrinsic, extravascular, and immune. Okay, so we can keep putting those into all those different classifications. Why is this? Because the patient develops the antibody. It's acquired, not inherited. The antibody is found in the plasma, so it's extrinsic to the red cell. Okay, And destruction in the spleen is extravascular because it occurs outside of the circulation. It's immune because an antibody causes it. Okay? So you have to look at all those different pieces in order to determine what type of hemolytic anemia it might be. So looking at extravascular hemolysis, this is where the macrophages recognize changes in old RBCs and phagocytize them to remove them from circulation. This is usually done in the spleen and the liver. So those macrophages in the spleen are very sensitive to subtle RBC changes. So we know that RBCs only last about 120 days. After around that time, they start to change, and those macrophages will be able to recognize that. We also have macrophages in the liver called Kupffer cells that can destroy severely damaged RBCs as well. So here's the process of extravascular hemolysis. It's actually kind of a fantastic recycling mechanism as well. This is something that you're also going to cover in the bilirubin area or the liver chapter within your chemistry class, but it's always nice to learn about it a couple different times. And I do believe we covered this a little bit in your analysis, so this should be somewhat of a review. But the first thing that happens is the macrophage, which is this big area up on the top right, will phagocytize that RBC. It'll break it down into various pieces. It's going to release some iron, but it's also going to have unconjugated bilirubin, which is actually biliviridin, that will be converted to unconjugated bilirubin. This heads then down to the liver where it becomes conjugated with a glucuronyltransferase. From there, some of that leftover will go to the intestines. Some of it will be excreted as fecal urobilinogen and converted to stercobilin. Those are the things we learned about in your analysis. But some of that urobilinogen from the intestine gets reabsorbed into the circulation, comes all the way up over here and down to the kidney, where it will be excreted in the urine. So, in a nutshell, if we have increased urine or fecal urobilinogen, it means that there's increased extravascular or increased cellular hemolysis going on. Okay. If you have a lot of hemolysis with the red cells, you'll have a lot of urobilinogen. There's really nothing else that causes you to have an increased urobilinogen. So that is really important to know as we move forward. So what I recommend you do now is to pause this video and try and draw out the process that we just talked about for review. Okay, go through the steps, draw the liver all the way to the kidney, the urobilinogen. It will help you create a mental memory of exactly what is happening here because we'll be referring to this quite a bit in the future. All right, next is intravascular hemolysis. This is the destruction of circulating RBCs with the release of RBC contents such as hemoglobin into the plasma. So when they are destroyed by any mechanism, whether it be usually some type of trauma, it could be having several clots, it could be that you have that prosthetic heart valve, whatever it may be causes the red cell to be destroyed in the vessel themselves. This will release a lot of hemoglobin into your circulation. This hemoglobin is going to be filtered by the glomerulus of the kidney, which could let a lot of iron inside the hemoglobin be lost from the body. So we're going to look at 3 different mechanisms that are in place to save this iron from being lost, because we do not want to urinate out our hemoglobin or our iron, which is contained inside the hemoglobin, right? We'd like to hang on to that. All right. So here's the haptoglobin process. Okay, another picture like you just saw. This is from your textbook. The RBC is lysed in the bloodstream and the hemoglobin will float out of the destroyed cell into the plasma. Okay, so you've got this free hemoglobin floating around. Haptoglobin is going to float by and pick up that excess hemoglobin to prevent it from being filtered by the glomerulus and excreted into the urine. Okay? This haptoglobin hemoglobin complex goes to the liver where it binds to the macrophage receptors that will internalize the haptoglobin hemoglobin complex. Inside the macrophage, the process of breaking down the hemoglobin is the same as the extravascular process that we saw a few slides prior. Okay? Haptoglobin is depleted in this process and is not able to be used. So if we have a lot of this intravascular hemolysis going on, haptoglobin will start to decrease rapidly. But you can see up here, this is what's new. From there, it goes back down into the exact same process that we just went through. It's just what does it do with that free hemoglobin. The next one is Hema Pectin, okay? With Hema Pectin, the RBC is lysed into the bloodstream, and the hemoglobin will float out of the destroyed cell into the plasma, just as we saw with the last one, right? Because they're being destroyed in the vessels. Iron becomes oxidized and forms methemoglobin. It goes from the ferrous, which is the good 2+ state, to a ferric, which is icky 3+ state. Okay, we always like ferrous because that's what it is in the hemoglobin. The heme breaks away from globin and binds to the protein hemopexin, which will prevent the glomerulus from filtering out the hemoglobin. Okay, so we want to hang on to that again. This hemopexin heme binds to the hepatocyte receptors in the liver and is internalized. The iron is salvaged and can be reused, and the rest of the broken down heme continues as in the extravascular process that we learned easier. Note here, hemopexin is able to be recycled and reused, unlike the haptoglobin that we just talked about. Okay? The hemopexin heme binds to the hepatocyte receptors and is internalized. Iron is then salvaged to be reused, and the rest of the breaking down heme continues as it does in that extravascular process that I had you guys draw earlier. Okay? Once again, hemopexin is able to be recycled and reused, unlike the haptoglobin. All right, the next one is metheme albumin. With metheme albumin, the RBC is lysed in the bloodstream, just like we've been talking about the last couple slides. It floats out of the into the plasma from the destroyed cell. Okay, iron becomes oxidized and forms methemoglobin, so it goes from a 2+ state to a 3+ state, as we saw. But in this case, heme binds to the albumin to prevent the kidney from filtering it. If you remember back to your urinalysis class, the kidneys should not be filtering out albumin. That glomerular basement membrane has that negative charge that repels away all of those large proteins they shouldn't fit through. So by it holding on to that albumin, it'll float right past and not be excreted in the kidneys. The heme will break away from albumin and join up with hemopexin eventually. That hemopexin has a higher affinity for heme than albumin, so that it's just one extra mode. Hemopexin will transport the heme to the liver. Heme undergoes the same breakdown as the extravascular process. Heme will break away from the albumin and join up with hemopexin. And hemopexin will transport the heme to the liver. And then the heme undergoes the same process that we saw earlier. So essentially, these all end the same. They just have a little bit of a different start in how we recycle things throughout the process. So sometimes we have excessive extravascular hemolysis. Most of the time, our RBCs display markers on their membrane to signal macrophages that they are old and ready to be removed. Pathological processes or diseases will have the RBC display those markers on their surface so that abnormal cells can be identified and removed. One example is Heinz bodies. Heinz bodies are aggregates of denatured hemoglobin. Okay, we talked about that this week. And I always think that denatured, like Heinz ketchup looks like denatured hemoglobin, which is why I made that association. So this binds to the inner surface of the RBC membrane, leading to the appearance of the markers on the cell surface. So it makes it easier to be destroyed by macrophages and such. And that concludes chapter 23. Make sure you move on next to listen to chapter 24.